It is 5:30. We are starting chapter 7, which chapter 7 is called Work and Energy. It's got a cool picture of Satchel Paige pitching from the pitcher's mound. That's kind of cool. In this chapter, we're going to learn about work, more specifically the physical concept of work as opposed to just the everyday word of work. But I'm going to try to relate the two so that it hopefully sticks in your head a little better. We're going to talk about a scalar product, which is also called a dot product and also called an inner product. And then we're going to widen our definition of work to include a force that could possibly vary as you push along some distance. And we're going to talk about the work energy theorem. As always, you should start by answering the chapter opening question. Let's go ahead and get started. First off, I want to motivate the idea of the physical principle of work, meaning a specific quantity that we can use in science. So to do that, I'm going to share my iPad screen with you guys. So this should come available in a second. And to motivate this idea of work, I'm going to draw two pieces of land, if you will, that represent basically yards to be mowed. Okay, because everyday life we talk about work, and one of the things that young people do to work is often they'll start off mowing grass or stuff like that. So it's a pretty apt explanation. So if you look, for instance, you might have a yard that is, let's say, actually, hold on here. One, two, three, four, five, six, and one, two, three, four. Oops, I don't like that one. One, two, three, four, like that, that, and that. And this might be, for instance, 80 foot. This stupid program, it automatically tries to make my drawings better. And when I write the number 8, it drew it as a snowman, I guess. A snowman with a blockhead. Anyways, let's get out of that. This is supposed to be 80 feet. And this one's supposed to be 120 feet. And what you might imagine in mowing this grass is you might imagine that maybe you have a 26-inch blade, lawnmower blade. That's a push mower. And having a 26-inch blade means that basically you're a little bit more than 2 feet. Normally, when you mow the grass, you actually have to exceed the length of the blade by a little bit, or excuse me, you have to overlap your blades a little bit just to keep from missing spots. So if I made it exactly 24 inches, that possibly would leave a little groove in between each row. So instead, what I'm saying is uh, we're going to take a walk this way 120 feet, and then that's going to cut out a 2 foot wide swath. It technically cuts out a 2 foot plus 2 inch wide swath, but then we're going to turn around and come back with another 2 foot wide swath. Again, it's a 2 foot 2 inch wide swath, so it's 26 inches, but we're leaving 2 inches of overlap, and then we do it again. And then we do it again, and so on and so forth. And in fact, what it takes, since we're using 24 inches of the blade, is it takes 2 feet. Therefore, uh, our mower will make, if you divide 80 by 2, you get 40, so it'll make 40 2 foot wide swaths, each 120 feet long. And that's what it's going to take to mow the grass. You're going to basically, you can imagine going due north, turning around exactly 24 inches wider than, wider than, or starting at 24 inches from the left edge of the property, and then walk back again, go to now instead of 24, you go 48 inches, and then go back and back and back. So it's going to take you basically 40 of those paths, 2 inches, 2 feet wide in each case, and each one's 120 feet long. So you would say that mowing that grass is a certain amount of work. And what we're trying to tie work to is things like force and distance and velocity and kinematic variables. Now, if we consider another lawn, let's do again a similar 120 foot deep lawn like this, but instead of it being uh, 80 feet wide, let's imagine it being 160 feet wide. So it would be basically here, 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 like this. And this side is 120. There I go again with the automatic filling in of the needed drawings. 120 feet by, of course, 160 feet. In this case, our mower will make, instead of 40, it will actually make 80 2 foot wide swaths, each 120 feet long. Okay. So you might argue that the lot on the right is twice as much work as the lot on the left. And the major difference between these two works was the total distance you traveled, because basically each swath was 120 feet by 24 inches wide. In the left case, you did 40 of them. In the right case, you did 80 of them. So thinking that this is twice as much work as the blue one, thinking the purple lawn requires twice as much work as the blue lawn, suggests that work should be proportional to distance. So we're using the symbol W for work, and just like we used it for weight before, but we shouldn't have any problem confusing those because they are going to have different units, and we're probably going to speak to them in different contexts. Now, that makes some sense that work is directly proportional to distance. You would say, for instance, a half marathon is half as much work as a whole marathon. So that seems somewhat reasonable and consistent with the everyday work definition of work. Another thing you might consider is, what if we mowed these two lawns, or let's say, what if we mowed the blue lawn with one mower, and then we mowed the blue lawn with another mower, but the mowers were different. So, for instance, consider one mower to weigh 100 pounds and the other to weigh 50 pounds. Now let's imagine this scenario where basically the 100 pound one doesn't necessarily do any better work. It's got the same size engine and everything, but it's heavier. It's got a built heavier deck and stuff like that. So that would tell you that you're definitely going to put, in some sense, twice as much force into it. And it would probably make sense for you to say, okay, in this case, then I suspect work is not only proportional to the distance, but it's also proportional to the work that I put in, or to the force that I apply to it. So in that case, I'm now going to say this suggests the 100-pound mower would require twice the work as the 50-pound mower. So that now we have work, instead of it just being proportional to distance, we're going to say it's proportional to force times distance. And I'll clean it up a little bit more. Specifically, what we're going to do is we're going to realize, for instance, if I'm pushing a mower, let's imagine that I have a mower that's got a big back wheel and a small front wheel, because those are actually kind of nice to use. And here's your motor, and here's your handle. And let's imagine that we're pushing like this, mowing the grass. Well, what that shows you is that you have a force acting this way. Well, that force breaks up into a component that is, in fact, downward and doesn't do anything to make the thing move along the distance d that we're trying to go. And then the other part is a component that is actually parallel to the distance that you're moving. So we're imagining, for instance, moving this lawnmower a certain distance d, and from that you can see maybe we shouldn't count in that purple component of force, the one that's pointing down, because that's literally making the job worse or definitely not making it better. And it's definitely a wasted component in some sense, because if I put the whole force completely horizontal, I could move a lot faster, get more work done. But instead, I'm pushing down on it. Pushing down on it means there's going to be a larger normal force. A larger normal force means there's going to be a larger friction force, and a larger friction force means it's going to be harder for me to push. So what we change the work to is, instead, work is going to be equal to, and I'm making it now an equal to, and this is basically the one of the equations. As long as the force doesn't change direction and doesn't change magnitude anywhere along the path, then we're going to say work is equal to the component of force that's parallel to the distance. Of course, you could also say it's equal to the component of distance that's parallel to the force, or you could also say, if this was the angle theta, for instance, down here, you could say that work is equal to, oops, I didn't want to write it that way. We could also say that work is force times distance times the cosine of the angle theta, because the cosine of theta times the force would give us the component of force that's parallel to d. Alternatively, if you drew the vector d along with the vector f, you could see that cosine of theta acting on d, being multiplied by d, would give us the component of d that's actually parallel to f as well. So that's the three versions of work that we've motivated, but this is only accurate as long as the force, and I'm writing it here as a vector quantity, does not change magnitude or direction along, well, along the displacement D. In other words, we're sort of picturing the displacement as being a straight line. It may or may not be a straight line, but the main thing we got to do, if we're doing it, whether it's a straight line or not, is we got to keep the angle between the force and the displacement path to be a constant, and we got to keep the magnitude of the force to be a constant over that whole path, whether it's a straight line, a curved line, or whatever. If we do that, then these formulas work, and that is our motivated definition of work, at least under those specific criteria. If I wish to take into account the fact that the force could change, the angle that the force makes with the displacement vector could change, I'm going to show you how to deal with that a little bit later. But right now, we're going to go ahead and use this to work out some physical problems where we can calculate work just to give you an idea. So let's start off with example 7.1, and it says work done on a crate. So example 7.1. Work done on a crate. A person pulls a 50 kilogram crate 40 meters along a horizontal floor by a constant force, FP equals 100 newtons, which acts at an angle of 37 degrees, as shown in figure 7.3. As shown in figure 7.3. The floor is rough and exerts a friction force, F friction equals 50 newtons. Determine A, the work done by each force acting on the crate, and B, the net work done on the crate. So what we're given is that the mass is equal to 50, and I'm going to add a third sig fig, so I'm going to call that 50 kilograms. The displacement D has a distance of 40. Again, I'm adding an extra sig fig, 40 meters. The force FP is equal to 100 newtons. So by me writing that decimal point, that's basically the same thing as saying that I not only have 100 newtons, but I have 100 newtons to 3 sig figs. Alternatively, I could have written 100.0 and just underscored that, and then that would also tell me that our sig figs is 3. So that's the key thing here. Now, in order to fix the 37 degrees, the 3 sig figs, I wouldn't want to make that 37.0 because that would miss the purpose of them using 37 degrees. The purpose of them using the 37 degrees is because they're trying to make you think of the right, what we call the 3-4-5 triangle. So I'm going to say theta is actually 36.8 degrees, because if you take the inverse tangent of 3/4, let me turn my calculator on real quick. Inverse tangent of 3/4, 3 divided by 4, close parentheses, is actually 36.87 degrees. So actually, I should probably call it 36.9. I forgot that that next digit was a bigger than 5, so 36.9 would be a better result. But there it is now in 3 sig figs. That's kind of helpful. And we also have the friction force, which I indicate with that fancy script F instead of a F with a subscript script F. So that's something I do. But anyways, that's 50.0 newtons as well. And specifically, I added another digit there. For part A, we want to know the work done by each force. So we want to know the work done by the friction force. We want to know the work done by the pulling force. We want to know the work done by the normal force. Or actually, I've been calling that F sub n. So let me go ahead and stick with that. So the normal force F sub n, and we want to know the work done by the weight. So I'll also say work done by mg, because obviously if I wrote W sub W, that might be a little more confusing, so I thought I'd not do that. And then part B, they want to know the net work done. So B, they want W net equals question mark. Now, in order to make sense of this, we need a bit of a diagram. So let me draw a diagram real quick. I'm going to draw a box like this. I'm going to draw it sliding over a surface. The mass is M. The force acting on it is going to be, this is going to be a force that's not parallel to our X or Y axis, so I want to use a color other than green and red. And in fact, I'm going to say it's FP equals 100.0 newtons. And that angle, of course, is theta that I just told you about. And now I'm going to draw a free body diagram to make some sense of what we got here. So that will allow me to determine, for instance, the normal force, which we obviously can't calculate the work done by the normal force unless we know what the normal force is. So I'm going to call this the positive y direction upward, the positive x direction to the right, and I'm going to say the mass right here is a point particle of mass m. I'm going to draw that blue vector again, and that's at an angle theta. And in this case, you might even want to go ahead and write it as not theta, but 36.9 degrees. and this is 100.0 newtons. Now, in addition to that, I have a normal force acting upward. So I'll draw that green, and that's F normal. I have a weight acting downward. Ooh, I have a weight acting downward, and that is mg. And of course, 50 times 9.8 is basically 490. Let me double check that. So 50 times 9.8 is equal to 490.0 newtons. Now, we also have acting on it a friction force, which, since we're pulling it to the right, the friction force must act to the left, and that friction force is 50.0 newtons. And now we've got to break the components of, or we got to break the blue vector up into components, and the components are going to be the horizontal x component, which is right here, and then the vertical y component, which is also positive and therefore points in the green direction. And from this, we know that, for instance, the sine of 36.9 degrees, we know that specifically is equal to opposite over hypotenuse, but we also know from the 3, 4, 5 triangle, if this is 3, this is 4, then this is 5, and this is 36.9 degrees, then we know that the sine of 36.9 is opposite over hypotenuse, which is 3/5, which is 0.6, but that's also equal to FP sub y over 100.0 newtons. Similarly, we know that cosine 36.9 degrees is equal to 4/5, which is zero point 0.8, but that's also equal to FP sub x over 100.0 newtons. Again, that extra zero is not a sig fig. Now we can break all this down. Obviously, if you multiply 100 times 4/5, you get 80. So this force right here is 80.0 newtons. And if you multiply 100 times 3/5, you get 60. So that's going to be 60.0 newtons is the y component. Now we have all the forces. I'm going to go ahead and use the summation of forces in the y direction is equal to mass times acceleration in the y direction. But as we've argued 1,000 times before, when you're moving an object horizontally like this, the y variable, the y coordinate is not changing, and y2 minus y1 is always going to be 0. So v, which would be y2 minus y1 over t2 minus t1, the average velocity would be 0. Now, if you consider some time later where it'd be y4 minus y3, say, and divided by t3, 4 minus t3, that was also going to be 0. So comparing those two, you get 0 minus 0 over t4 minus t1. That's the acceleration, and the acceleration, of course, is 0. So with that in mind, what we see is we get Fn, which points up, so it's positive, plus 60.0 newtons, again points up, so it's positive, minus 490 newtons is equal to 0, and that tells us that the normal force is in fact equal to 430.0 newtons. So I just pull the 490 to the right, that'll become positive 490, and then I pull the 60 to the right, that'll become negative 60. 490 minus 60 is 430. That's how I got that. Now I'm able to actually calculate the work done by each of those forces. So first off, let's go ahead and work solution. And the formulas we're using is work is equal to F parallel, work is equal to F parallel times D, or work is equal to D parallel times F, or work is equal to F times D times the cosine of the angle between them. But when you write it that way, it has to have a diagram so you'd understand what theta is. So let me show you what theta is in this case. You're taking force, which is a vector quantity, you're taking displacement, which is a vector quantity, and you're saying the angle between them when they're tail to tail is theta. So you can't really use FD cosine theta without this picture, or at least without it in your head. Okay. Now we're going to go ahead and calculate the work. Let's start off with the work done by the pulling force, FP. So work, FP, is equal to FD cosine theta. That's what I'm going to use. So I'm going to say FP in this case is, well, actually, no. We know that D, let me draw D on here. I can draw it this way by putting a little blank mark in here. And then what we'll say is D is the vector that points from here all the way to here, and that distance is 40 meters. But now you can see that if you move the FP vector, theta would be the angle between them. So you can use that theta as the theta we want. But alternatively, we could use the component of F that's parallel to D like that. If I choose to use that, then which component am I going to multiply by the 40 meters? Is it the 80 or the 60 that I'm going to multiply by 40 meters? Anyone? Yes, the 80 is the one that's parallel, so I'm going to write down 80.0 newtons times 40.0 meters. And that's it. By writing F parallel times D, I don't have to have the cosine function. So 8 times 4 is 32, and then 80 times 40 would therefore be 3,200. So this is 3,200 newtons times meters. Now, the dimensions of work are the units of work suggests that there the dimensions are units of force times the dimensions are units of distance, which is a newton times a meter. But it turns out we define 1 Newton meter to be 1 joule. Now that's named after James Prescott Joule. Joule is his name, is the way his name is spelled. And they are that family is the family that's responsible for a good deal of understanding we have from thermodynamics, and specifically, they were in the business of making cannons for the government. They also made beer, and there's in fact in Great Britain still a beer called Jowls that was made by their family. But that's all related to that. And if you've had chemistry or earth science before, you know that 1 calorie is equal to 4.184 joules. And that is what we call the mechanical equivalent of heat. And James Prescott Joule is the one that did the experiment that showed that those two quantities, that's not just a conversion factor. That's the way we learn it, but it's not a conversion factor only. It's actually a huge uh, re-understanding of the world. They thought before this that mechanical energy, like potential energy, kinetic energy, which we're getting ready to learn about, was one sort of energy, and we measured that, for instance, in joules. And then they had another type of energy called the caloric, which was heat energy that could go was like a fluid inside of substances, and it would flow from a hot object to a cold object. That was measured in calories, and they thought those were two entirely unrelated quantities until James Prescott Joule was able to show that they are truly related, and that's where the term joule came from. Just to give you an idea, 1 joule is about as much energy as it takes to lift a red delicious apple, a really good sized red delicious apple, from the ground to the height of a kitchen table. So that's about how much energy a joule is. That's also about how much work a joule takes, because it turns out that we can define energy as the ability to do work, and we can define work as anything in which a force is applied over a distance. So, for instance, driving a nail is work because you have to not only apply force to the nail, that force has to be applied as the nail moves through some distance. And if you need to consider a really small amount of work, like you're talking about atoms and stuff like that, then you could say, well, imagine using a very microscopic, let's say 1 atom wide needle as a nail, and you're pushing that into hot butter. Then you can then see that, oh, okay, well, that's still a force over a distance, even though it's a really, really small amount of force and a really, really small amount of distance. It still is meets the criteria of work. So you can think of any of those small processes as work as well. So now that we have all that, we can continue working on with this. Now, just to show you, if you wanted to actually calculate, let's do it alternatively. We can say work FP is equal to 100.0 newtons times 40.0 meters times cosine 36.9 degrees. And when we do that, we say 100 times 40 times cosine 36.9, and that gives us 3,199 joules, which obviously is only good to that, to 3 sig figs, which gives us exactly the 3,200. So you can see that either way works. So we now have one part of the answer. I'm going to circle that and say this is W sub FP. Now I want to calculate the work done by friction. So the work done by friction is equal to the friction force parallel times D, or it's equal to the friction force, or let's write it in a different order. It's work equal to the component of the displacement that's parallel to the friction force, or it's equal to the friction force times D times the cosine of the angle between them. I think it's most instructive here to use the FD cosine theta formula here, because what you have to realize is the displacement vector is actually, I drew it as a double-headed arrow. I really shouldn't have done that. I was initially just going to draw the length and show it a double-headed arrow, but when I wrote D vector under it, that made it sort of not correct. So let me just take that off right there. And now I will put that little bit of, oops, I'll put that little bit of vector back in it. And now you can see that the vector extends from the front edge of the box to 40 meters away from the front edge of the box. And it's a vector that points to the right. You see that the friction force, so the displacement force is pointing to the right, the friction force is pointing to the left, so the angle between them is in fact 180 degrees. That's the difference in putting them tail to tail, which is what you need to do to use this formula. So in this case, I'm going to say 50.0 newtons times 40.0 meters times the cosine of 180 degrees. We know the cosine of 180 is -1. We know that 5 times 4 is 20. So this is going to give us 20 because the 10 in the 50 and the 10 in the 40 gives us 100, and then 20 times 100 gives us 2000, which is 1,000. So that's 2,000 joules. And of course, one of those digits is not a significant figure, so it's 200, and then the last digit's not. So that's our work done against friction. And oops, I left off the negative. So I'm going to say work done for friction. I'm going to go ahead and box that off. And I would just want to point out to you that whenever you have a force that points one direction and the displacement that points somewhat the opposite direction, meaning the only component that's parallel or anti-parallel of the force to the actual displacement, when those two are anti-parallel, you're always going to have a negative amount of work done. So keep that in mind. And this is why you see that the cosine of 180 gives you that. Okay. And it's also sort of like it's more like the friction force is losing to the FP force. So it's losing, and we've got to keep account of exactly how much it lost. So it doesn't make sense for it to just be called zero. You have to call it something less than zero so that it can take away from what you got for the thing that was greater than zero. So the 3,200 is the newtons that the FP put in, or excuse me, is the joules that the FP put in, but the -2,000 is the joules that the friction force took out of it. So you can think of it that way as well. So that's the work done against friction. Now we got the work done by the normal force, or actually, I should say the work done by friction, not against friction. The work done against friction would be positive. In this case, we actually might say positive 200 because it's some force that's just fighting the friction. Just to do that, that would be the 2,000 joules. But now we're going to do the work done by the normal force. And this is a case where we're going to use the normal force times g times cosine of the angle between them. And in this case, the normal force we found was 430.0 newtons. The displacement was 40.0 meters, and then the cosine of theta, theta in this case is 90 degrees. It doesn't make any sense. It doesn't really matter whether it's positive 90 or negative 90. Notice I didn't draw an arrow on the end of my theta there because it really we haven't found the usefulness to make the difference between theta pointing up or theta pointing down like that. So we're just going to say it's cosine of 90. And of course, the cosine of 90 is equal to 0. So that means the work done by the friction force is 0.0 joules equals work done. I said friction force, sorry about that, is the work done by the normal force. So that's that. Now we're going to do the work done by the weight. And that is the work done by mg is equal to mgd cosine theta. The mg we know is 490.0 newtons, but of course the zero after the decimal place is not a sig fig. The d is 40.0 meters, and the cosine again is 90. The theta is 90 degrees. Again, maybe you'd call the cosine of positive 90 for the F normal, then you'd have to call the theta of the weight negative 90. Either way, it doesn't really matter. So in this case, we're again going to get 0.0 joules is equal to the work done by the weight mg. So that's all the work done that we were asked to do in part B. I now need to explain to you what work net is. I said part B. Why did I say that? That was all that was required to do of you for part A. Part B is calculate the work net. And there's a couple different ways you can define work net. You can say work net is equal to the summation from I equals 1 to N of W sub I. In other words, every force that's acting on this object, uh, W1 would be considered for force 1, W2 would be considered for force 2, W3 would be considered for force 3. However many forces you have, that might be a capital N, then all you have to do is add them all algebraically. Some will be positive, some will be negative, some will be zero. You sum them up, and that is W net. But you could also say that W net is equal to the summation of all the forces times the displacement times the cosine of the angle between them. And in some sense, you might even have to integrate that cosine inside of it like this. You might say, okay, well, we're going to take f cosine theta and we're going to add up all of those. Summation from I equals 1 to N of f sub I theta sub I times D. So that's another way you could do it. You just sum up all the forces and then you let that, or all the components of the forces that are parallel to the displacement vector, add all those up and then multiply that by the magnitude of the displacement, and that would give you the scalar quantity that is the work. So that's two ways we could actually do the W net, and that's going to come in handy later. Right now, I'm just going to use the leftmost way. So for part B, I'm going to say W net is equal to WFP plus W friction plus WFN plus WMG, which I think you can see is going to be 3,200 joules plus negative 2,000 joules plus 0 joules plus 0 joules, which gives me ultimately just 1,200 joules equals W net, like that. And that's the answer. Okay. Any questions on that? All right, we'll learn later that it turns out if the total work, the W net that you do, if that's actually greater than zero, then that's going to be equal to what we call the change in kinetic energy. So by doing this particular experiment, if we actually carried this out with something that produced a 50 Newton force using 100 Newton force at 36.9 degrees above horizontal, we would find that the change in kinetic energy was 1200 Newton meters or 1200 joules. And in fact, that change in kinetic energy is one half times the mass of the box times the velocity squared. And the initial velocity is zero, so the initial kinetic energy is zero. That means you could set this 1200 equal to one half m times the velocity of the box squared, and you would solve for the velocity v of the box, and that would tell you how fast the box is going at the end of the 40-meter distance. So that's something we're going to learn later. That's called the work energy theorem. Now that we have that, let's look at another example. In this case, it's example 7.2. So example 7.2. Actually, before I do that, does anybody have any questions on example 7.1? I went really sort of overboard making sure I explained everything, but if you have questions, I want to ask it. I want you to ask it. Okay, it looks like you guys are getting it. All right, so example 7.2 says work on a backpack. It says A, determine the work a hiker must do on a 15.0 kilogram backpack to carry it up a hill of height h equals 10.0 meters. Excuse me. As shown in figure 7.4a. Determine also B, the work done by gravity on the backpack, and C, the net work done on the backpack. For simplicity, assume the motion is smooth and at a constant velocity, i.e. acceleration is zero. So we're imagining this as being just enough force to overcome any friction forces or whatever that's there, and we're not even taking into account the friction forces, but we're just applying it so slowly that basically the walker's just going to slowly move up like this to the top of the little incline that happens to be 10 meters high. Okay. I'm going to write down exactly what we have here. We know the mass of the backpack is equal to 15.0 kilograms. And that means that the weight of the backpack, which is m times g, is going to be 15 times 9.8. And that gives me 147.0 newtons is the weight, just because we're going to need that anyways. We also know that the height of the hill is 10.0 meters. We're not actually given the angle theta. That's going to come be relevant in a second, but the main thing is I'm going to draw a diagram so it'll make some sense to you. The diagram is this. You got a horizontal line, runs into an incline, and then the incline flattens out to another horizontal surface. And I'm drawing this just to give you an idea roughly where a triangle is. This is h is equal to 10.0 meters, like that, from here to here. And they're calling this angle right here theta. Okay. Now, what's going on is we have a person walking like so, carrying a backpack. Backpack, backpack. Swipe or no swiping? I'm living the good life. Okay. So there's the hiker. And then the hiker, of course, is going to walk up to the end as such, like that. And that's what we're actually examining. To make sense of this, we need to sort of draw a free body diagram, not necessarily to discover any forces, but that might allow us better to understand the angles between the various forces and other vectors. So, for instance, one of our vectors is a displacement vector. So, I hesitate to call this an actual free body diagram because I'm getting ready to draw a displacement vector on it. So what I'm going to do is I'm going to draw the displacement vector sort of dash so it doesn't look like it's part of the diagram, but it allows us to put it in space with the other forces so that we can make some sense about it. What we're looking at here is this displacement vector is d and goes like that. and this angle right here is theta. Now, what we have is a force acting upward, and that is the force that the hiker, F sub h, puts on the backpack, and then the force of gravity on the backpack points down, and that force is 147.0 newtons, like that. So, one thing you can see, and this is part of the reason why I covered a little bit of geometry last time, this line is vertical, this line is vertical, so that means this line and this line are parallel, and then this line, the displacement vector, actually traverses those two, and then that tells us that this angle and this angle are alternate interior angles because they're both inside and they're on opposite sides of the transverse. So what that also tells us is that this angle right here is also theta. So now we can see that the angle between the F sub h, the force the hiker applies, and the displacement vector is the angle theta. And we can also make sense by if we put the displacement vector tail to tail with the weight vector, we'd see that this angle right here is 90 minus theta, and then this angle is 90 degrees. So what we get is the total angle here is 90 plus 90 minus theta, which equals 180 minus theta degrees. So we could use an actual trig identity to figure out what that angle is or what the cosine of that angle is. And we'll cross that bridge when we come to it. But basically what we found was it's 180 minus theta is the total angle between the mg vector and the displacement vector. So now what we are asked to do is to calculate A, the work done by the hiker. So A, we want work done by the hiker equals question mark. B, we want the work done by gravity, which I'll say work done by mg is equal to question mark. And then C, we want the net work done, so we want W net. Our solution here is W is equal to F parallel times D, but it's also D parallel times F, but it's also F times D times cosine of the angle between them. Of course, you've got to think of that diagram when you're using it, but now we're ready to roll. So let's start off with part A. Part A, we want to know the work done by the hiker. So the work done by the hiker is the force applied by the hiker times D times the cosine of the angle between them. And as we showed, the angle between them was in fact theta. So we can go ahead and say FH, which happens to be the force applied by the hiker. And we can see that from the summation forces in the y direction equals mass times acceleration in the y direction. Again, in this case, it might seem a little odd, but we specifically were told that we're going to move this so slowly that it's not going to accelerate. So that's how we know, even though the y actually changed, we're not accelerating it. We're going infinitesimally small amounts of motion at a time until the net result is we've reached 10 meters higher than we were and some number of meters to the right that we don't know. Because of that, we can say that H minus 147.0 newtons is equal to 0, and that tells us that FH is in fact 147.0 newtons. So that's what we're getting here. We can put that in 147.0 newtons. And then here's the neat part, D cosine theta. If you look at the diagram, you can realize that D is this distance, and this distance is H, and let's just call this distance X, and in fact that's a right triangle, but you'll notice that D cosine theta is in fact equal to, since cosine theta is equal to adjacent over hypotenuse, the adjacent is H and the hypotenuse is D, so D cosine theta is just equal to H. So now that we have that, we know this is h, which is equal to 10.0 meters, and therefore we know that the work done by the hiker is 1,470 joules equals the work done by the hiker. Anybody have any questions on that? Now you can look back at it in retrospect and see some obvious things, and I highly recommend you do that. What you'll notice is the object moved left and right, but it also moved up and down. Uh, you can think of the component of D that happens to be parallel to F as only that H, because if you think of the vector D as made up of this X component right here and this Y component right here, you'd see that the H is the component of F that's parallel to D. So you'd get the same thing there. This part right here would just be H times F. So you can get that without even doing the d cosine theta as well. That's a whole nother way. So that's why I tell you it's not only the force component that's parallel to d times d, it's also the d, the displacement component that's parallel to f times f. And that is a case where you've actually seen where that worked out. Now we can do the work done by the weight, which is part B. So let's get started with that. B, the work done by the weight, mg, is going to be mg, and I can write it like this and say component parallel to D, or I can write D parallel times mg, that would work as well, or I can write mg times d cosine theta. That part works as well, and in fact it gives us something that's kind of instructive, which we'll use next chapter. The d cosine theta we already worked out as h, so it turns out the actual work done here is mgh. Later we're going to learn that that happens to be the potential energy, and in this case the work done only goes into increasing the potential energy by an amount mgh. In this case, though, we're seeing that the mg is actually pointing in the opposite direction. So you'll have to basically say instead of cosine of theta, we can say that it's going to be the cosine of 180 minus theta. So if I want to just compute it using a formulas like we know that the mg is 147.0 newtons, and then we know it's d times the cosine of 180 minus theta. Now I got to work that out. We're going to say the W sub mg is equal to 147.0 newtons times d. And now I've got to figure out what the cosine of 180 minus theta is. I can pull up a trig identity. I'm actually going to do it on the web though. Uh, Cosine, let's do it this way. So when you do a sum of angles, the cosine of 180 minus theta turns out to be negative cosine theta. And that tells us something specific. We're going to get now d times negative cosine theta, which gives us again negative mg d cosine theta. And remember, we said the d is actually equal to h, so it's actually negative mgh is the work done against it. So that gave me that formula that I told you about being the change in potential energy, but it's the negative of that. And that's also expected because gravity's pulling down when the object's making a net movement up. So they're in opposite directions, so you would expect it to be negative. That being said, we're going to get that the total work done is 1470 newtons times -1, because the cosine of 180 minus theta is negative cosine theta, and then times d cosine theta, which was h, which was 10.0 meters. So we get -1470 joules equals the work done against gravity, or by gravity, excuse me, like that. So that is the actual answer for this case. And as I said, that is the H right there. Any questions on that one? All right, now part C is just the W net, and I'm going to calculate W net the same way I did last time. I'm just going to add up the W's. So for part C, we're going to say C W net is equal to W of the hiker plus W due to gravity, and that is equal to 1,470 joules plus negative 1,470 joules, which equals 0.0 joules equals W net. And they told us specifically that we were supposed to assume the motion was smooth and that there was no acceleration. And that is good because we're ultimately going to show that the net work is equal to the change in kinetic energy. And if you assume that the backpack was sitting perfectly still at the bottom of the hill before you started to walk up to the hill, and that it was sitting still when it got at the top of the hill, then the change in kinetic energy, which is again 1/2 mv squared, would be zero, because it's the initial velocity zero, the final velocity zero, so both of those are zero. So we'd expect the net work to be done to be zero, and that's what we got here. So again, we've already started making things consistent with what we call the work energy theorem. Anybody have any questions on that? All right, there's a really good example, 7.3 here. I'm going to do that, and this is just a conceptual example. And it says specifically, does the Earth do work on the moon? The moon revolves about the Earth in a nearly circular orbit with approximately constant tangential speed, kept there by the gravitational force exerted by the Earth. Does gravity do A, positive work, B, negative work, or C, no work at all on the moon? So in order to make some sense of this, I'm going to use the feature that my program has where it can actually draw a circle really well, and then I'm going to draw yet another circle really well for the orbit. So I'm going to go like here to, let's say that's up 2.5, that's down 2.5, so something like that. So I'm going to say like that. There's a rough circle, and that's supposed to be the orbit of the moon, and that's supposed to be the moon up top. So here's Luna, the moon, and here is Earth, E. And what we see is the velocity of the moon is this direction, and that's actually tangential to the orbit, which we're pretending to be a circle. And then, of course, we know the force of gravity is actually pulling this way. That's the force due to gravity. And you can see that these two vectors have to be at 90-degree angle to each other. Well, the displacement D is approximately equal to V times delta T, right? And in fact, they're parallel. This is a vector equation, so that D, the displacement vector for any small amount of time, delta T, is going to be V times delta T. And you can see that that, of course, is parallel. So that tells us again that the vector D, displacement in this case, is also parallel, at least on that small scale. It's parallel to the velocity and therefore also perpendicular to the force. Since the gravitational force is perpendicular to the small displacement, the work done has to be 0 because work equals FD cosine theta, which equals FD cosine 90 degrees, which equals 0. Okay, so yes, when we actually assume that the moon is traveling a circular orbit, then at all points the velocity is perpendicular to the force, and therefore there's no work done on it. If you actually had an elliptical orbit, let's imagine, for instance, a very extreme elliptical orbit. I'm going to try to draw one with this computer program in hopes that it can do something nice, but I'm not sure it can. There you go. That's pretty good. So we might say, for instance, the moon is right here. And if we look at the planet when it's here, the planet when it's, dang it, it will not let me draw a circle there. Let me just draw a circle without the help. Okay. So when the planet is here, what you see is the velocity is this direction, and the force of gravity, which I meant to draw in green, the force of gravity is this direction, and you can see that angle is actually bigger than 90. So in this case, in this elliptical orbit, at that particular point in time, it's not 90 degrees, it's this additional 90 plus theta, and therefore work is being done by the gravitational force in slowing down the planet as it gets closer and closer to perihelion. And then when you get over to the other side, say right here, the velocity again is tangent to the ellipse, and the friction force, or excuse me, the gravitational force in this case it actually is less than 90 degrees, so it's speeding it up. So speeding it up, this one's slowing down. And you can't speed up or slow down unless you apply a force in the direction of motion or in the opposite direction of motion. Opposite direction of motion makes you slow down. The same direction of motion makes you speed up. So you can see that in an elliptical orbit, you're going to have, in fact, some work being done by the gravitational force in slowing down and speeding up. And of course, it happens again out here as well. So when the planet gets here or when the planet gets here, you'll see other quantities as well. It's even more obvious with these far out ones because you can see there's your tangential velocity and your gravitational force is this way. So clearly it's speeding it up. On this side, the velocity tangential is that way. And of course, the gravitational force is along this line. So it's slowing it down again. So this is slowing and this is speeding up. So you can see in all four of those, there is actually work being done, but in the case of the moon, there's not been work being done. So the actual work being done is none at all. Any questions on that? All right. Now it seems very helpful for us to make a little bit more sense of that work formula, work equals FD cosine theta. It actually looks like a mathematical construct that we've discovered in creation of vector calculus. So it's called the dot product or inner product. The, oops, the dot product. I'll say the scalar or dot or inner, oops, product. Now, what you could do is you could put a dash after the dot and a dash after the scalar and call it a scalar dash product or a dot dash product or a inner dash product. We normally don't use the dash or the hyphen or whatever between the dot and the product or between the product and whatever word, but those are three different names we could use. And basically, what we define the dot product as is A dot B is equal to A times B times cosine theta. As you can see, just from the idea of work is force times distance times cosine theta. That was crying, telling us, hey, if this operation of the magnitude of a force times the magnitude of the displacement vector times the cosine of the angle between them, that might be something really handy. So they decided to create something called the dot product, and that's the formula for the dot product. I should also say that when you write a vector as A without the vector symbol, that's the same thing as the magnitude. So this is the same thing as magnitude of A times the magnitude of B times the cosine of theta. And then in some math classes, you'll see that the magnitude of A is written like this with double absolute value bars, and then times cosine theta. All of those mean the same thing, and they all have the accompanying diagram A, B. The angle between them when they're tail to tail is theta. Okay? Now, there are some neat little features about the dot product. For instance, the dot product A dot parenthesis B plus C is equal to A dot B plus A dot C. Not only that, if you took A and dotted it with B, a scalar times a vector B, plus C, a scalar times a vector C, then you could just call this B times A dot B plus C times A dot C. Oops. And this right here refers to the linearity. Oops. Linearity of the scalar product. We say that it's a linear operation, so that whenever you take a dot product of a vector times a scalar, you can just pull all the scalars out in front of the dot product and then let the dot product act only on the vectors themselves. So with that in mind, we can say, therefore, if A is equal to A sub x I hat plus A sub y j hat plus A sub z k hat, and B is equal to B sub x I hat plus B sub y j hat plus B sub z k hat. If we had that, then A dot B is equal to A sub x I hat plus A sub y j hat plus A sub z k hat dotted with B sub x I hat plus B sub y j hat plus B sub z k hat. And using those last two principles that I showed you, how you could break up sums and distribute it over negatives, what that's telling us is the distributive property works perfectly well with the dot product, just like it did with regular algebra and regular multiplication. So when I go to do this dot product, I'm going to take the x component, and I'm going to let it hit the x component of B, and then I'm going to let it hit the y component of B, and then I'm going to let it hit the z component of B. Additionally, I'm going to let the y component of A hit B sub x, I'm going to let it hit B sub y, and I'm going to let it hit B sub z. And then finally, I'm going to take the z component and let it hit B sub x. I'm going to let it hit B sub y, and I'm going to let it hit B sub z. So you can see that we should get 9 terms. Now, what are those 9 terms? Let me work them out. It's going to be AX I hat dot BX I hat plus AX I hat dot B y j hat plus a x I hat dot dot b z k hat. Those are first 3 terms, and I know I got really small in there. Let me see if I can make this a little easier to see so it doesn't look so crummy in there. Uh, I'm going to say this is equal to AX I hat dotted with BX I hat plus AX I hat dotted with BY J hat plus AX I hat dotted with BZ K hat. That's the first three terms from the blue arrows. Now the second three terms is going to be A Y J hat dot B X I hat plus A Y J hat dot B Y J hat plus A Y J hat dot B Z K hat. That's the second three terms, which are the red ones. And then finally, I can do the last three terms, which is going to be A Z K hat dot B X I hat plus A Z K hat dot B Y J hat plus A Z K hat dot B Z K hat. So that looks like a holy mess, but it's really not as bad as you think, because now we can use the linearity of the dot product to see that it's AX BX times I hat dot I hat plus AXBY I hat dot J hat plus AXBZ I hat dot K hat plus AYBX J hat dot I hat plus AYBY J hat dot J hat plus AYBZ J hat dot K hat. So that's my second set of three. And now I can continue with the third set. That's going to be A, Z, B, X, K hat dot I hat plus A, Z, B, Y, K hat dot J hat plus A, Z, B, Z, K hat dot K hat. Now, here's the big thing. Since A dot B is A times B times cosine theta, we can see that, I'm going to write it right here, I hat dot I hat is equal to J hat dot J hat is equal to K hat dot K hat, all of which equals 1 times the cosine of 0 degrees, which is just 1. So whenever you have I hat and I hat, that's going to be 1. Whenever you have J hat and J hat, that's going to be 1. And whenever you have K hat and K hat, that's going to be 1 as well. Now, if you try I hat dot J hat, which also equals J hat dot K hat, which also equals every other combination. So IJ, JI, IK, JK, IK, all those different ones where they don't match, they're all going to give you 1 times the cosine of 90 degrees, which equals 0. So that means this, using green now, this is 0, 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 and this is 0. So what we've just figured out is that A dot B is also AXBX plus AYBY plus AZBZ, and that was another version of the dot product. So just starting with the dot product being defined as AB cosine theta, which notice looks just like the work formula. we were able to find from that A dot B is also the product of the like components in X plus the product of the like components in Y plus the product of the like components in Z. And that's a scalar. That's why they call it a scalar product. So never, ever, ever are you supposed to actually give me a vector, or excuse me, give me a dot product that has an I hat or a J hat in it. It's supposed to be a scalar. So let's do an example so you can have an idea of one, how to do dot products, but two, how we can use dot products. So let's look at this one. This is a uh, dot product example. So what we're going to do is I'm going to draw two vectors. This is my y-axis and this is my x-axis. We don't have to have three components of every vector. We can just do dot products in two-dimensional space. That works as well. You're just not going to have an AZ or a BZ. That's okay. That's what we're going to do here. And this is very instructive. So what I'm going to do is first imagine that I have a vector that is, actually, let me make this a little bigger than what I have here. I'm going to continue this straight line down like this. And I'm going to say this is my x-axis. And what I'm going to do first is I'm going to consider a nice little triangle like let's say the one that has a x component that's 1 and a y component that is square root of 3. So the square root of 3 is about 1.73. So I'm treating two squares as 1. So this would be 1 and this would be 2. And therefore 1.73 would be almost halfway between 1.5 and 2, but it'd be a little bit smaller than that. So I'm going to say square root of 3 is right there roughly. And this vector is going to be right here, and I'm going to call that vector A. And this angle right here, hopefully you already recognize it, but this angle should be 60 degrees. Now I'm going to compare that to another vector, and this vector is going to be the 3, 4, 5 vector, or the 3, 4, 5 triangle. So 1 is there, 2 is there. Actually, I'll draw this one. I'll still use blue, so I'm going to put this as 2 and this as 3 and this as 4 and so on and so forth. But specifically, now I'm going to say 1, 2, 3, 4 like that. So the 3, 4, 5 triangle would be 3 to the left and 4 up. So now this other vector is going to be a vector from here to here, and that's vector B. And of course, this angle right here has to be, in this case, it's the 53, it's one, or excuse me, it's 90 minus 36.78. So that's 53.22 degrees roughly. Okay, so that tells you that the angle between them, which maybe I'll call phi, is equal to 60.00 minus 53.32, or excuse me, 53.2 degrees. And I don't know why I'm even showing that math. Obviously, you could do that subtraction yourself. 53.22 minus 60, or 60 minus 53.22 would be 6.78. So phi is equal to, oops, phi is equal to 6.78 degrees roughly. Okay, so that's something we know. What I'm going to do now is calculate the actual dot product of A and B, and then I'm going to use another form of the dot product of A and B to calculate the dot product of A and B, and I'm going to use that to solve for the angle between them, because that's one of the key things that you can use the dot product for, is you can use it to find the angle between any two vectors. So what we know here based on our drawing was that A is equal to, clearly it had an x component of 1, so that is 1 I hat, and it has a y component of the square root of 3, so I want to write that as the square root of 3 times j hat. We also had the vector b, and b had an x component that was 3, so that's going to be 3 I hat, and it has a y component that's 4, so that's going to be 4 j hat. From this, we can tell that the magnitude of A, let me go ahead and write that back in red. The magnitude of A, which is also just plain A, is equal to the square root of 1 squared plus the square root of 3 squared. That gives me the square root, actually I'll keep it all under this one. That gives me the square root of 1 plus 3, which is the square root of 4, which is 2.00. So that's the magnitude of A. That's going to come in handy because remember our dot product is A times B times the angle between them. We're also going to find that the magnitude of B, which is given by B, and the absolute value bars are just plain B like this. This is going to be the square root of 3 squared plus 4 squared, which equals the square root of 9 plus 16. And of course, that means it's the square root of 25, but the square root of 25 is 5.00. So that's our magnitude. Now let's calculate A dot B is equal to, now we also know A dot B is AX BX plus AY BY plus AZ BZ. Of course, these two vectors have no Z components, so this is how that's going to work out. The X component of A is 1. The X component of B is 3. The Y component of A is the square root of 3. The Y component of B is 4. And the X component of A is 0, and the Y component of A is 0. So we're going to get 3 plus 4 times the square root of 3, which we can get a approximate value of that, but that actually works pretty well as well. Just for the record, I'll say 3 plus 4 times the square root of 3 is about 9.928. So that's 4 sig figs. That's enough. So we now know that the dot product is 9.928. Now we also know that the dot product is A dot B equals AB cosine theta. And in this case, that means it's 2.00, no units. These are pure numerical vectors, so they had no units, times 5.00 times the cosine of the angle between them, which I've drawn that angle as phi, so it's probably best that I not write this angle as theta. It's probably best that I go ahead and plug in the angle phi right there, and I used green just to indicate that that's the phi that we're talking about on the diagram. So what we get here is that A dot B is also equal to 10.00 times the cosine of phi. So if we write A dot B is equal to A dot B, just, formally saying what I'm doing, therefore we can reach the conclusion that 3 plus 4 square roots of 3 is equal to 10.00 times cosine of phi, and that tells us that phi is equal to the cosine inverse of 3 plus 4 root 3 over 10.00, which is approximately cosine inverse of 9.928 over 10.00. And if I do shift cosine inverse 9.928 divided by 10, that gives me 0.9928. That gives me 6.880. And of course, we only use really three sig figs for everything. In fact, so that should be roughly 6.88 degrees. We found it to be 6.78 roughly, but that's, obviously uh, up to the appropriate number of sig figs. So we can see that this function can be used, this dot product can be used to find the angle between two angles, between two vectors. But more specifically, we use the dot product to find a component of a vector that happens to be parallel to another vector. We use the cross product, which we'll learn about later, as a operation that gives us the component of one vector that happens to be perpendicular to another vector. So if you're wanting to pick out like components, i.e. parallel components, you use the dot product. If you want to pick out unlike components, components that are perpendicular to each other, then you're going to use the cross product. And that's the operation that we use dot products and cross products for. The cross product is also called a vector product, in case you haven't heard of it before, and it's A, and then it uses the big X for multiplication cross B, and that gives you a vector A cross B that happens to be perpendicular to both A and B, whose magnitude is equal to AB sine theta. We'll cover that later, but that's the whole purpose of all these dot products and cross products in terms of vector calculus. It was made up because they were so convenient and allowed us to do things. So, for instance, we can find, if you wanted to find, for instance, the x component of, let's say, vector A, let's say, to find the x component of A, take its dot product with I hat. Now, if you took it with just any vector in the x direction, it's going to be convoluted because it's going to have the magnitude of that vector in the x direction as well in it. But if you take it with an I hat, then the component of the x vector, the vector that points in the x direction, is just one, so it's not going to harm anything. So if we do that, let's look what happens. If I say A dot I hat, that is equal to magnitude of A times the magnitude of I hat times the cosine of the angle between them. That's not very helpful because we're going on the assumption that we just know A is 1 I hat plus 3 J hat, but we can use A sub X I hat sub X plus A sub Y I hat sub Y plus A sub Z uh, I hat sub Z. That's another way we could do it. But when you do that, you see that the x component of A is in fact just 1, and the x component of I hat is just 1. The y component of A is the square root of 3. The y component of I hat is 0, and the z components of both are 0. So you end up just getting 1, which is exactly the dot product, or excuse me, which is exactly the x component. Sorry about that. Now you can also use the other version, and that would be the magnitude of A times the magnitude of I hat, which would be the magnitude of A we found was 2.00. The magnitude of I hat is 1.00. And then the cosine of the angle between the A vector and the I hat vector is, of course, 60 degrees. And if you took 2 times 1 times the cosine of 60, you would get 1.00. So you see both of those ways we did it were able to give us the x component. If we wanted to find the y component of A, we just dot it with j hat. If you wanted to find the z component, you dot it with k hat. Anybody have any questions on that? Thanks, Nathan. All right, so that's a introduction to scalar products, vectors of basically two vectors multiplied to give you a scalar product, and you can see now how the vectors come into play when we calculate the work, because work is really just F dot D. So now we know work is equal to F dot D, provided F does not change over D. In other words, anywhere along D, the direction and magnitude of F is not changing. If that's the case, then work can be given by work is just equal to F dot D, which we just showed you how to do that. Now I have to go a little further and show you how do we deal with this in the event that we want to calculate work and the force actually changes along the way. So work done by a variable force. In this case, what we're imagining is we're starting from point A and we're going to point B like that. And what we notice is that the force, for instance, right here, the force is this way. Right here, the force is that way. Right here, the force might be that way, and 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 all that. So all of that is a problem. If you see that the force, which in principle is a vector field, so it's literally assigns to each point in space a vector quantity, so that when you're at any point along the path, which is made up of D here, basically you got a bunch of little displacement vectors from A to somewhere really close to A, and then from that spot to somewhere really close to it, and then from that spot to really close to that, so on and so forth, then you have a little bit more of a problem. So what we do is we imagine breaking this path up into itty bitty components. So we're going to say this path from A to B is going to be made up of this little vector from here to here, and then this little vector from here to here, and then this little vector from here to here, and so on and so forth. If we break it up small enough, then what'll happen is the force, which is varying everywhere, that force will be basically a constant over that whole little space. So we could say there's a single vector F that corresponds to this first one. There's a single vector F that corresponds to the second one. There's another one for the third one, another one for the fourth one, another one for the fifth one, so on and so forth. And then what we could do is each of these little blue guys are d sub 1 vectors. They're really, really small. And each of these little purple guys are f vectors evaluated at d sub 1, something like that. So what we could do is take the little dot product that we get for that small region, that little itty bitty di, we take the dot product of f with that. And if f changes very much from one end of that little d sub I to the other end, then we redivide the path up into smaller parts until it stops changing. And then when it changes, when it stopped changing, then you can just do the regular dot product for that itty bitty part. Well, I'm going to call that itty bitty part basically a, I should use blue here. I'm going to call that itty bitty part a d sub L. It's a differentially short length of a vector L. Okay, so it's a differential vector. And then, of course, the work done to that one part, W sub I, would be F sub I dotted with DL sub I, and I would subscript that I just because I have to divvy it up into, an infinitesimal or infinite number of subsections. So we're doing basically that Riemann sum thing. We're breaking up the path into individual little vectors, and those little vectors are so short that each little force doesn't change over it. So we can use just our normal formula, which is force times distance times the cosine of the angle between them. Now all we have to do is add up each little contribution so that W total is equal to the summation from I equals 1 to N of Fi dotted with DL sub I like that. Well, we could do it finitely like that, and maybe you break up a single path into 1,000 points, but that's 1,000 little individual calculations. What we might do instead is use the mechanics of calculus to divide it up into little Riemann sums and let that basically go to infinitely many so that every time you do it will always be small enough. In that case, we get W is equal to the integral of f dot dl, and that's our general formula of the work. So this is the absolutely correct formula for W in all cases. So you can actually just work that out for any force. And technically speaking, it is what we call a path integral or a line integral. So it's actually an integral that takes the place along a path, and you have to evaluate the integral, the f dot dl. You have to evaluate that on the curve. So for instance, if the curve was y equals x squared, if you had any values of y in the integral, you would replace them with x squared. And if you had a dy, you would replace that with 2x dx and that kind of stuff. That's what makes it an actual path or line integral. As luck would have it, most of the time we integrate in the positive coordinate direction, so there's really no problem for just not even realizing it's a path integral or a line integral. You just do the calculation and it gives you the right answer. So I will show you, especially in the second semester, I will show you how you have to deal with these path integrals and line integrals. But right now you can just sort of follow your book's lead and understand that, hey, there's something about this. If I have to choose weird directions, like I'm going in a negative coordinate direction, I have to put more thought into it. But the general rule is, and y'all might want to like save this sentence or record, rewind the video, listen to this part alone. But here it is. When you go to calculate the work done as an integral of f dot dl, I told you that's a path integral. That path integral, you have to let the integration process know which direction you're going. And the direction you're going is indicated either by the dl vector, because it points in the direction of integration, or by the limits of integration from A to B, for instance, because A is your first point and B is your last point. But you only do one of those. What you're supposed to do is, if you want to make the DL show your direction of integration, then you define DL pointing in the right direction, and then you let your limits of integration go from small coordinate to large coordinate, period. No matter what, you just say small coordinate to large coordinate. Even if you're supposed to actually integrate from r equals 5 to -3, you're still going to say the integral is from -3 to 5. That's if you choose to let the DL show the direction. If, on the other hand, you choose to let the limits of integration show the direction, then you'd integrate from 5 to -3, but the DL would point in the positive coordinate direction. So that's the two choices. Either the DL points in the positive coordinate direction and the limits of integration tell you the direction you're going, or the limits of integration go from small coordinate to large coordinate and the DL tells you which direction you're going. That's the big key to doing line integrals. The good news is the vast majority of these problems, you're just going to be integrating in the positive coordinate direction. So you end up getting that the limits of integration and the DL both point in the positive direction. So there's no harm in that because they're both supposed to, the default is supposed to be pointing in the positive coordinate direction anyways. All right, now that we have that, I'm going to do something really quick regarding W net. So this is the work energy theorem. Oops. The work energy theorem. So what we're going to do is we're going to try to calculate W net, which I already told you about before was the sum of all the individual works. But I also told you that other way, which is the work done by the sum of all the forces in the coordinate direction, blah, blah, blah. So work net is going to be equal to F net dot dl. Now F net, remember, Newton's second law says the summation of the forces is equal to mass times acceleration, which I'm going to choose to write dv dt in this particular case. But I want to point out that this left-hand side is the same thing as F net. So the summation of the forces is what we recognize as F net. So with that in mind, this integral becomes the integral of the summation of the forces dotted with dl. Now, since it's equal to the left-hand side of Newton's second law, it must also be equal to the right-hand side of Newton's second law. So it's going to be m dv dt dotted with dl. So in other words, the summation of the forces became m dvdt. Remember, dvdt is just another word for acceleration, but it shows the nature that the acceleration is the derivative of a vector quantity called the velocity, and the velocity, of course, is the derivative of a vector quantity called the position. So now that we have that, now here's the neat thing. It turns out that if you're like me, when you took calculus, you learned that the derivative symbol dy dx meant the derivative of y with respect to x, and you just thought of that dy dx as a convenient little symbol that we use. But in fact, it looks a lot like a formula. It looks like a change in y over a change in x, and in reality, it is. It turns out that the dy's, in some sense, can be thought of as what we call a mathematical one form. A one form is sort of the counter example to a vector or something, but you'll learn more about that if you take vector calculus or calculus on manifolds or something like that. None of which I had. I just had to teach myself because they didn't offer those courses at a couple of places I went to. But either way, what you realize then is once you realize that dy over dx is not only the symbol for the derivative of y with respect to x, but it's also a differential change in y divided by a differential change in x, and it's also a one form dy and a one form dx. When you do that, then you can see things like, hey, I bet it's okay if I change the order of my dv and my dl because there's a dot product there, and dot products are actually commutative. A dot b is equal to b dot a, at least in real space. Later, when we learn about quantum mechanics, that's going to go to the wind. But what that allows me to do is the integral of m, and now instead of dv dt, I'm going to say dl dt, and then that's going to be dotted with dv. So all I did was reverse the roles dv and dl. Now, hopefully everybody recognizes what dl dt is. Can anybody tell me what physical quantity dl dt would be? If you don't know, because you haven't seen that formula before, think of the units and I bet you can guess. I hope y'all aren't hearing all that noise of me swallowing and stuff, but if you do, I apologize. Okay, so DLDT is a length divided by time. Normally, length, yeah, very good, Samuel. Length divided by time is a velocity. And in fact, DLDT is a more accurate definition of velocity because when I say DYDT, that's technically the velocity, the Y component of velocity. And when I say DXDT, that's technically the X component of velocity. But if I just took DL, which could point in any direction, over DT, then I'm calculating the velocity in any direction. So I'm actually calculating the velocity by dl dt, which is more accurate or precise than dx dt or dy dt. So this quantity right here, the dl dt, is actually v. So what we have here is the integral of mv dotted with dv, and of course a differential change in v is just a really small v, so they're actually parallel, so the dot product becomes moot and you end up getting the integral of mv dv. And of course the integral of mv dv is 1/2 mv squared, and technically we're supposed to integrate this from since I'm integrating in v, we would integrate that from v initial to v final. So that means my limits of integration are v initial to v final. Notice that that's in the positive coordinate direction, so we're at least doing part of it by default. And in fact, what we get is 1 half mv final squared minus 1 half mv initial squared. And in fact, that allows us to define a term called kinetic energy, which is also called the energy of motion. That's what kinetic means, is motion in some sense. So kinetic energy is in general defined to be 1 half mv squared. Now, I will tell you that that's the case in Newtonian or what we call classical physics. If you ever get to speeds approaching the speed of light, even say within 1% of the speed of light, then there's a different formula you're supposed to use, and you'll learn that in relativity. I'll tell you now that basically kinetic energy is gamma minus 1 times mc squared, where gamma is equal to 1 over the square root of 1 minus v over c quantity squared. That's the more general expression, and it does actually reduce to 1 half mv squared in small velocities. So it's actually the more correct formula, but it's ugly to use, so you don't want to use it. So just be advised, if we were doing relativity, you'd have to use that K, but in this case, we get this K. So we've now gave you the definition of kinetic energy, and we've also solved the work energy theorem, or we've derived the work energy theorem, and the work energy theorem says that W net is equal to the change in kinetic energy, where change in the delta, that delta symbol always means final minus initial. So that would be K final minus K initial. That is our work energy theorem. So that's the work energy theorem. Now we have that. And now you can remember, for instance, when we did the hiker, right here, we got that the W net was equal to zero, and that's completely consistent with them telling us, hey, assume that the motion is very steady and that there's no acceleration. No acceleration means whatever velocity it had, it's going to have that at the beginning, and it's going to have the same velocity at the end. So 1 half mv squared initial is equal to 1 half mv squared final. So k final minus k initial is zero, and that's why we get the zero there. Additionally, when we did the other one, we got W net was 1200, and what that tells us is 1 half m v final squared minus 1 half m v initial squared, which was zero, is equal to 1200 joules. That means that v final would actually equal the square root of 2 times 1200 joules divided by the mass, which was 50.0 kilograms, and then we got to take the square root of all that. So I can say 2 times 1200, oops, and then I can divide that by 50, and that gives me 48. The square root of 48 is, in fact, 6.928 meters per second. So this is totally, of course, unrelated to the example we were doing, but now we have an example where we use the work energy theorem to conclude that the box that we were sliding against friction actually increased speed, and it went from 0 meters per second to about 7 meters per second. So that's part of what the work energy theorem tells us. Now, with that in mind, let's go on and do some examples with this new formula for work. So I'm going to start off with telling you that now work is equal to the integral of f dot dl. That's the formula. What we're thinking about here is f is going to be some f sub x I hat plus f sub y j hat plus f sub z k hat, and dl is going to be some dx I hat plus dy j hat plus dz k hat, so that f dot dl would be f sub x dx plus f sub y dy plus f sub z dz. That's really the process that we could go through in the most general case. But in general, that would mean work is equal to the integral fx dx plus the integral fy dy plus the integral fz dz. And again, that sort of takes you further away from recognizing this is an integral over a path and all that kind of stuff. But we are supposed to do it from xa to xb, from y, excuse me, that one should be ya to yb, and from ZA to ZB. That is the most general way that work could be done. But what we might want to do is apply it to a simple formula. And that simple formula that we're going to use is called Hooke's law. And this is Robert Hooke, who was an arch enemy of Newton. What he found was that the force, and your book is calling it F sub S for force due to a spring, but Hooke actually found that for any object. For instance, if you take a pin or a piece of rebar or a 2x4, and if you apply a force F to it, it's going to change its length by an amount X because it's being compressed, and that x is directly proportional to the force, meaning if you double the force, that x will get twice as large. If you triple the force, that x you get 3 times as large. But it's a very small amount when you're talking about a 2x4 or a piece of PVC pipe or a piece of rebar or something like that. So it turns out if we tried to do that in a lab setting with freshmen and sophomore college students, then we'd have to be working with forces on the order of a ton, and that gets really, really dangerous. So it turns out that because it works with compressing a solid object or stretching a solid object, it's also going to work with a spring, only the X is going to be a lot larger. So that's why they're saying that. And specifically, they say F is equal to negative KX. And what you're picturing here is, let's imagine that this is our X coordinate system. Let's imagine, for instance, that we have a floor right here and a wall right here, and that what we're dealing with is a spring that is in equilibrium right there at x equals 0. That's equilibrium. Now, if you apply a force and pull the string out to a position x, then what happens is the spring gets stretched like that, and the force that's actually that you actually feel from that is a force this way. That's the F sub S, and the X was of course measured this way. So the negative is just saying, hey, if you pull in the positive x direction, the force is going to be in the negative x direction. That's why the negative's in there. So most of the time when you're working with F equals a kx, which is called Hooke's law, you can just drop the negative. But if you have to plug Hooke's law into an equation and you're wanting to calculate something about the force that the spring applies to the object when it's been stretched, then you have to include that negative. Other than that, you can just use F equals kx and always take the magnitude and not worry about it. Now, with that in mind, what we want to do is calculate the work a person does to stretch or compress a spring from its normal unstretched length xa to which equals 0 to an extra length xb equals x. So that's what we're going to do. And the way we're going to do it is this: work is equal to the integral of f dot dl. And I'm imagining that coordinate system that I have drawn right there.
What I'm doing though is I'm calculating the force that I'm applying. So the force that I'm applying is going to be pulling it to the right to stretch it. And of course, the actual stretch is going to go to the right. So I don't want any kind of negative there. I'm going to say the force, of course, has to be equal in magnitude to k times x because that's what Hooke's law tells us. But it's not going to point in the negative direction. It's going to point in the positive direction. So I'm going to say k times x pointing in the I hat direction. That's the actual force. Now, here's where I told you when you do a line or a surface or a path integral, you have to either let the dl point in the direction of integration, or you need to let the limits of integration point in the direction of integration. In either case, the other just points in the positive coordinate direction. So in this case, I'm going to let dl define the direction I'm going. The direction I'm going is in the positive x direction. So I'm going to go ahead and write in dx I hat. As you can see, that was one of the possible terms of dl was dx I hat, and I chose it in the positive direction because I'm integrating in the positive direction by stretching the spring. Okay. Now I've chosen DL to indicate the direction of the integration. Now I just have to choose the X going from small value to large value, which lo and behold happens to be the same direction as if I would have chosen to choose the direction or to indicate the direction by the limits of integration. So in this case, I'm going to say from X equals 0 to XB equals X. Okay. So this is why most of the time you don't get pinged by doing it wrong, because it turns out that as long as you're going in the positive direction, the DL and the limits of integration are both in the same direction, so it doesn't matter either way. Now, we can take the dot product here. Remember, we learned that the dot product is a linear operation, so that means we can take the integral from x equals 0 to x of just taking all the scalar parts, which would be kx dx out in front, and then we have I hat dotted with I hat, but I hat dot I hat we learned was 1. And of course, the integral of kx dx is 1 half k x squared from x equals 0 to x, which equals 1 half k x squared. Now, if we did the same thing, except in compressing it, watch what would happen. So compressing. So work is equal to the integral of f dot dl. And this is where I told you again, you either need to do the integration. You have to let us know which direction the integration is, either by using the dl or by using the limits of integration. So this time I'm going to use the dl to indicate the limits of integration. So, or excuse me, the dl to indicate the direction of integration. So the force is still going to be, in this case, I have to compress it. So the force is going to be in the negative x direction. So I'm going to get negative kx I hat. Now that just means that it's pointing in the negative I hat direction. That's why the negative is there. Now I'm going to integrate in the negative x direction, but I'm going to indicate that with the limits of integration instead of with the dl. I could do it the other way, and I will, so I'll show you. But in by showing the limits of integration, what I'm going to do is say that the dl has to be in the positive coordinate direction, which is dx I hat, and then I'm going to integrate this from x equals 0 to x equals negative x. Okay, so now instead of stretching at a distance positive x, I'm compressing at a distance negative x. So this is limits of integration show integration direction. Positive coordinate direction, like that. And therefore, we get, in this case, negative kx. And this one's going to be a little funny because it's going to get a negative in there, but because of the negative kx, but that's okay. I'm just trying to show you the process. Now, if I wanted to do it for by showing show integration direction with dl, then in this case, I would do W equals the integral of f dot dl like that. This is going to be, again, I'm pushing in the negative x direction, so that's going to be negative kx I hat. And then my dx is going to be negative dx I hat. But in this case, I'm going to take from small coordinate to large coordinate, so I'm going to integrate from negative x to x, and that negative is so close to the x, it's hard to tell that it's a negative. So that's the way you would set it up, showing that showing your integration direction as the limits of integration, whereas the other one was by showing with the DL. So now we see by limits of integration, I go from 0 to negative x, but by showing in DL, I say the DL is negative dx I hat. So that's the two different possibilities. The main thing we're getting out of this example, which is just the part above the line here, is this result. The work done in compressing or stretching a spring by an amount x is 1/2 kx squared, and the k is called the spring constant, and it has units of newtons per meter in general. Now we only got 10 minutes left, so now I got to show you a couple of examples. First off, I'm going to do example 7.5 because that's super easy. So example 7.5 says work done on a spring. A person pulls a spring in figure 7.10, stretching it 3 centimeters equals X max, which requires a maximum force of 75 newtons. How much work does the person do? And then B, if instead the person compresses the spring by 3 centimeters, how much work does the person do? So what we have here is X max is equal to 3.00 centimeters. That's me just adding another sig fig. And F max, because that's the one that causes the stretch, X max is equal to 75.0 newtons. And then for part A, we want to know the work done. And then for part B, if compressing W equals question mark. So for part A, I'm going to say work is equal to 1/2 kx squared, but I'll also have to make use of, let me go ahead and write it this way by starting with solution just so you guys will remember. We're going to say W equals 1/2 kx squared, but that also depends on the magnitude of the force being equal to k times x. So F equals k times x gives us 75.0 newtons is equal to k times 0.0300 meters, because we're not supposed to use things in centimeters, obviously. And from this, we get K is equal to 75.0 newtons divided by 3.00 times 10 to the negative 2 meters. Obviously, 75 divided by 3 is 25, but that's going to make 2,500 newtons per meter is our spring constant, and that's one extra digit beyond the sig figs. So now I have the spring constant. This is typical of how we solve the problems. They give you enough data to determine K, and then they ask you something that requires you to know K. So now we're going to do the work part, which doesn't require any integration. We just have to go 1/2 kx squared, because we learned that whether you're compressing it or stretching it, it's always going to be 1/2 kx squared. So we say 1/2 times 2,500 newtons per meter, that's one extra digit, times 0.0300 meters squared. So when I do this math, it's zero point 0.5 times 2,500 times zero point 0.03 squared, and that gives me 1.125 joules is equal to the work in compressing.
And obviously, we only had three sig figs, so we'd have to call that 1.13. Or your book only used two sig figs, so they call that 1.1. Now, for part B, it's the same thing, except it's actually the first one was stretching, the second one was compressing. So let me stretch. Now, compressing gives the same formula. So work is equal to 1 half K x squared, which again is 1 half 2,500 newtons per meter times 0.0300 meters squared. In this case, you might put the negative in there, but you see that squaring it is what happens, so it's still going to come out to be positive, and we're going to get 1.125 joules equals work compressing. So this time it is actually written as compression. Any questions on that one? Example 7.6 is pretty easy. We only got a couple minutes. Basically, what we're given is f of x is equal to some f0 times 1 plus x squared over 6 times x0 squared, like that. And we're told that f0 is 2.0 newtons. We're told that x0 is equal to 0.0070 meters. And we want to know the work done in going from x1 equals 0.010 meters to x2 equals 0.050 meters. And we want to know how much work is done. Work is equal to the integral of f dot dl is our solution. So that's what we're working with. So work is going to be equal to F0 times 1 plus 1/6 x0 squared in the bottom times x squared, like that, times dx I hat, because obviously the fact that it's a function of x only tells you that this is the component of a f in the x direction probably, and that's what we're assuming here. So the dl only picks out the dx I hat part, and this would be I hat there as well. So this becomes f0 out in front, the integral of 1 plus 1 over 6 x0 squared x squared times dx times I hat dot I hat, which is just 1. So this becomes f0 times the integral of dx from x1 to x2 plus 1 over 6 x0 squared integral x squared dx from x1 to x2, like that. That gives us f0 times x from x1 to x2 plus, now the integral of x squared is 1/3 x cubed, so this is going to become 1/18 x0 squared times x cubed from x1 to x2, and that ends up giving us f0 times, now we're going to do x2, which is 0.050 meters minus 0.010 meters, plus 1 over 18, and then the x0 is 0.0070 meters squared, and then times 0.050 meters cubed minus 0.010 meters cubed. You can see, hopefully, that the meters cubed with the meters squared in the bottom is just going to give us meters, which matches what's in the top. And then we plug all these numbers in, the 2.0 newtons times the 0.040 meters plus the 18, let's say 1 divided by parenthesis 18 times 0.007 squared in parentheses. This gives me a really big number, 1,134 meters to the negative 1 power, and then 0.05 cubed is
0.000125 meters cubed minus 0.01 cubed is 0.000001 meters cubed, like that. All of this, once you do the math, turns out to be 0.36, and I think I got 25 was the last digit. 12, 3612. So 3612 joules is the work done there. And that's the answer. Okay. Now, we only have like 2 minutes left, but I'm going to go ahead and call it. I'm going to do an example with the work energy theorem just so you'll have it on there. You're welcome to leave. Of course, you always have, you're always free to leave at any time. I want to remind you guys that you're not doing, actually, you guys are my Tuesday. Oh yeah, that's right. You guys are in my class that has a lab tomorrow. We don't have lab tomorrow. Remember, that's the day off that's normally spent for the online test or for the face-to-face test, excuse me. But you do have an online test and a face-to-face test that's due by Sunday. So make sure you get those done. They have to be done with a lockdown browser, Respondus monitor, Respondus lockdown browser. You have to have a webcam. You have to have good, reliable Wi-Fi. You have to have a computer that can run Canvas, Respondus lockdown browser, Respondus lockdown monitor, or excuse me, Respondus monitor, and the Canvas quiz. All of that has to be done. If you cannot do this on your own sometime between anytime Saturday to anytime Sunday, then you need to set up something where it can be done either Friday, and you'd have to let me know because you're only supposed to be given the day of Saturday or Sunday to do it. But if you need the extra time so you can get to a testing center, then you can do either Friday or Saturday. That's the only 2 days that are available, and you need to make that appointment immediately because you might not get a spot otherwise. So if you can't do this on your own with your own computers and stuff at home, then make sure you make an appointment at the testing center. And if you need to do that on Friday instead of Saturday, then you need to let me know because I've got to make up a separate test for you to do at the testing center on Friday. If you're doing it on Saturday, it's not a big deal. It'll be ready, and this testing center will have the important information. So good luck, everyone. Have a good day. I'll wait for the last person to leave, and then I'm going to solve a example involving the work energy theorem, and then I'll call it a day. You're welcome to stay and watch, but you don't have to. All right, so now I'm going to go ahead and work a work energy theorem problem. The normal example, or the most typical work energy theorem problem, is the typical one of you see a car accident has occurred, and you see skid marks, and you see the police officers out there measuring the length of the skid marks. Well, you can actually use the length of those skid marks to realize, hey, a friction force of kinetic friction was applied over the whole time those brakes were causing the tires to skid. So if you measure the length of the skid, then the work done by the friction force would be the friction force, which you can calculate using the kinetic coefficient of friction for the surface that the road's made out of and the surface that the tires are made out of, and using the normal force for the vehicle, which you can look up based on its manufacturer. You can say the normal force, or excuse me, the friction force is going to be the coefficient of static friction, mu k, times the normal force, which if it's a horizontal road, it's not tilted, then it's just going to be m times g. And then the force, the work done would be that force times d times the cosine of the angle between them. D is the length of the skid marks, and the cosine of the angle between them is the cosine of 180, which is a negative. So the total work done is going to be the negative of the friction force times the distance or the length of the skid mark. That's going to give you a negative number of joules, which is newtons times meters, and then that's going to be equal to the change in kinetic energy. And of course, if you're skidding from some initial speed, which is what the police officer wants to know, to some final speed that's zero. So the kinetic energy final is going to be zero, but the kinetic energy initial is going to be 1/2 mv initial squared. So in that case, just so you'll know, you'll end up getting mu kinetic times -1 times M times G times D. This is W net. And remember that negative came from the cosine of 180. That's where the negative came from. And that's equal to the change in kinetic energy, which equals 1 half mv final squared, but it came to a stop. So the final velocity is 0 minus 1 half mv initial squared. And that's what you're actually looking for. So we end up getting negative mu sub k mgd is equal to negative 1 half mv initial squared. But notice with this, the m's actually cancel out, so you actually don't even have to look up the mass of the vehicle. All you have to know is the coefficient of stat or kinetic friction between the road surface and the actual tires, and you need to know the length of the curve, and the negatives drop out as well. So I can say this negative makes that negative a positive, and now we can say that the final velocity or the initial velocity, which is to check whether or not the person was speeding when they got in the crash, that can be taken by finding the square root of 2 times mu k times g times d and then dividing it. Actually, I think that's it. 2 mu k g d. Yeah, that's it. There's no division whatsoever. So that is the actual formula for the initial velocity of the vehicle. That's a very typical work energy theorem problem. So I'll say typical work energy theorem problem. But you can also tell that that means the length of your skid is going to be proportional to the square of your velocity. That's why it's so important that you have a very slow speed, for instance, around school zones, because if you double the speed, you quadruple the braking distance. And that means, instead of you going 3 meters to come to a stop, you might go in fact, what 12 meters, and that would be the difference between running over a kid or not running over a kid, which would be really bad. Now I've sort of highlighted that particular example just from word of mouth, but now I'm going to do another example. This is example 7.7, and that's the one that I was really shooting for here. That's the one that I decided to stay after for. Example 7.7 says a 145-gram baseball is thrown so that it acquires a speed of 25 meters per second. What is its kinetic energy? And B, what was the net work done on the ball to make it reach the speed if it started from rest? So what we have here is M, which has to be put in kilograms, is 0.145 kilograms. We know the initial velocity 0 meters per second. We know the final velocity is supposed to be 25 meters per second, like that. And for part A, we want to know what is the kinetic energy, K final equals question mark. And B, we want to know what was the net work done. So like that, the solution requires two equations here. One, K is equal to 1 half mv squared. That's one equation. And W net equals the change in kinetic energy is the other equation. So let's start off by calculating A. The kinetic energy is equal to 1 half times 0.145 kilograms times 25 meters per second squared. This is going to be zero point 0.5 times 0.145 times 25 squared. That gives me 45.31. And that's actually two extra digits. So that's 25.31 joules is equal to the final kinetic energy. And then B, they want to know B, W net equals question mark. Well, we know W net is equal to the change in kinetic energy, which is equal to the kinetic energy final minus kinetic energy initial. But the kinetic energy initial is zero, so we get that the net work is 45.31 joules, and that's it. Okay, so I gave you basically two sort of examples to work far as the work energy theorem goes. I think that's more than enough experience. We've now completed chapter 7. We will start into chapter 8 next week. And remember, you guys have a test over the weekend, online test as well as a face-to-face test. Plus, I sent out an email earlier about people making up missed tests. That has to be done, so make sure y'all do that as well. Have a good weekend. And again, I'm going to wait here till the last person leaves in case anybody has any questions. And I see Sam did stay. Do you have a question, Sam, or are you just hanging out to check that out?
Oh, okay. Can you hear me?
Yeah, I can hear you.
Yeah, I sent you an email about the thing,
The
the appointment I sent at the test center.
Yeah,
So I
I
just
saw that. Didn't you send that? Was it yesterday?
Yeah, it was yesterday.
Yeah, I did get it. I thought I'd sent back a reply saying got it, but I might not have if
uh
you're asking me about
I
it.
probably I probably didn't look at it.
Okay. Yeah, I got it. So you're good to go, and you did get your appointment Saturday, so everything should be good to go. Whatever time you show up, they'll have a password so they can get you in it, and that should be it. Actually, you don't even need a password. You'll just be there with their ability to watch you on the camera and all that stuff. You are allowed to bring your own equation sheet, but you're going to have to,
Okay.
show it to me, and they're going to have to give it, make a copy of it and send it to me so that I can make sure it is the same as my equation sheet.
Okay.
All right.
Which is that the regular physics equation sheet with all the physics equations, not the book ones?
Yeah, it's if you look in the helpful
Uh
documents and links module, there will be a section and there's a document in there that says 241 PH or no, it says 241 Calc Physics allowed
yeah, that's
equations
one.
dot PDF. So if you just print that out and bring it in, then that automatically is the right one, and they'll just take a photograph of the front and back and send
Okay.
that to me just to verify that it's the same one. That way you don't have to scroll down to the bottom of the test and look at the electronic version and scroll back up to the question.
I so I see it's the calc physics allowed equation sheet. I'm
Yep,
pretty
that's the
sure
one.
that's yeah, the white page. Okay.
Yep.
All right, awesome.
All right. Have a good one. I hope you do well. I hope everybody does well. And have a good weekend. Stay safe.
All right, you
Mhm.
too.
Thanks, Sam.
All right,
Bye bye.
bye.
All right. So that's it. Have a good one, everybody. Enjoyed having you. Bye bye.